Welcome back. Our last topic in this unit on limits and continuity is how we define a continuous function. Again, all this stuff is leading up to us being able to define a derivative for you. And one of the topics that the AP exam does like is to know where derivatives do not exist. And one of the keys is that a function must be continuous at a point for a derivative to exist at that particular point. So that's going to be the first thing you're going to look for. So continuous functions, you have seen this stuff before. Let's talk about types of continuous functions first, or types of discontinuity. If we have some sort of piecewises, that kind of thing. Let's say we have a graph, and let's just call it a parabola, and then we get there and we're missing a point and it keeps on going, and let's say the point lies up here. This is a point of discontinuity, what we call a point of discontinuity. Sometimes it's called removable. Removable discontinuity, and like I said, we'll get into each of these algebraically in just a little bit. Another one you might see is an absolute value function. Let's say I have an absolute value function, divide it by itself, and it jumps up something like this. This is called jump discontinuity. And then similar to our last video on limits to infinity and then vertical asymptotes. If we have a vertical asymptote, I have an equation something like this. We can't remove that discontinuity. This is infinite. Infinite discontinuity. So you should be familiar with the types of discontinuity. The AP folks won't ask you it, but you should know which one is which, and I'll try to algebraically show those to you. They will ask you, and what you are responsible for is the definition of a continuous function. Three parts. Number one, f of x must be defined. Number two, the limit as x approaches c of f of x must exist. Let's go back to number one for 7. F of x is defined at x equals c. And then finally the third one, and this is the one that breaks down a lot, is the limit as x approaches c of f of x must equal f of c. So it has to satisfy all three of those conditions for it to be continuous. Sometimes people will get a little bit tripped up. On the last one. Excuse me. Or they'll have a hard time with go ahead and graphing like piecewise functions. Let me do an example, and we'll talk about what let's say we have this. Let's look at kind of a similar one we did before. Let's say we have something like this. F of x equals x squared minus 9 over x minus 3 if x is not equal to 3. And let's say it equals 2 if x equals 3. So we looked at something like this a little bit earlier. And remember, what we can do is we can simplify this. So I'm going to simplify this a little bit, because if I factor that, the x minus 3's will cancel. So really it's x plus 3 if x does not equal 3. And it's 2 if x equals 3. So when I sketch the graph of this equation has a point of discontinuity at 3, 6. It's discontinuous at 3, 6, because if I put 3 in here, I would get 6. It has a y-intercept at 3. It's this line, something like this. And then at 3, based on the second part of the piecewise, is down here at 2. So what ends up happening is that's not a removable discontinuity, but is a point of discontinuity. The point falls off the graph, and the part of the definition of continuous functions that's not satisfied is that last part, because the limit does exist, the limit's 6. The point does exist, the point is at 2. So f of 3, the first part of the definition, is 2. That's fine. The limit as x approaches 3 exists. That's 6. The part that doesn't work is that these are not equal to each other. So since these are not equal to each other, this is discontinuous. We look a lot at continuous functions. We do continuous functions many different ways. And one of the things that you'll be asked is you'll be asked to like figure out like where are these functions continuous, and because that's where the derivative is going to be defined. So let's say I have something like, I don't know, let's say I have something like this. F of x equals 2 over x squared minus 4. First of all, I can rewrite this as 2 over x plus 2, x minus 2, to simplify it. And what ends up happening is that the question would be worded on what domain is this function continuous? There's a couple of different ways of writing it. If this is f of x, I can't remove any of these points or anything. So it has a vertical asymptote at -2. It has a vertical asymptote at +2. So the function is going to be discontinuous at -2 and +2. In calculus, we like to write that as negative. It's continuous on the interval from -infinity to -2, union with -2 to 2, union with 2 to infinity. Notice that I didn't use any brackets on any of these. It's exclusive of these points. Back in Algebra 2, you might have written it as like all real numbers except x cannot equal -2 and +2. The AP folks, if they ask you a question like this, they'll accept either of those answers. So they'll accept, in their opinion, any right answer is correct. So you're all good. All right, so that concludes our unit on limits and continuous functions. And we'll be using this in our next topic of derivatives to define what a derivative is and then make sure that the derivative exists at certain points. We'll finish up clarifying for you on continuous functions. We'll review a little bit and have a test in just a couple of days. Best of luck.